Good morning to all of you. Last class we have been discussed about forced vibration. I have given one example how a oscillator is oscillating. If it will be stop after some times, it will be called as the damped harmonic oscillator. And if we are going to give a continuous force from the outside to that oscillator, it will be oscillate continuously up to infinite time, and then it will be called as forced vibration. Then it will be called as force vibration. So these are the notes we have been already discussed. So you have to follow this note, and up to I think we have been discussed up to this equation, right? This equation we haven't right. So today we are going to discuss about the solutions of this equation, and the one part is complementary function and another is a particular solution. So coming to the next page, it will be the complementary function or it will be transit state. Transit state. So putting RHS of the equation number 2, we can found the two roots uh, of the hence the solution it will be like this, and hence the solution will be the solution what we have been found in case of damped harmonic oscillator, because this is equation is nothing but so called damped harmonic oscillator. Already we have been discussed and we have been solved all the things. So at last we found this is the solution of the damped harmonic oscillator, so no need to solve so many things once again. So here beta is nothing but omega square minus b square root over the so-called amplitude a0 decays means decreases exponential with time in case of damped harmonic oscillator, and the motion therefore after sufficiently long time it will stop, so that it will be called as the transient state. Transient state. Okay, so after sometimes it is stopped, so that it will be called as transient state. So, but particular solution is indicates about the steady state motion. Steady state means it will be a constant type motion, means there is no variations, or there is no going. We are going to expect that it is going to be stopped after sometimes. So here, when the external periodic force is applied on the oscillator, then the driving force tends to make the oscillator oscillates with the frequency of a driving force, and oscillator itself wants to oscillate with its natural frequency. But after sufficiently long time, the transients completed, and ultimately the oscillator performs oscillation at frequency of applied force. This is called the steady state. That means here you can that the last class I have been also explained. Suppose one oscillator is oscillating, after sometimes it will be stopped. It will be stopped. That means it will be so called damped harmonic oscillator. But if I am going to give continuously force, then it will be oscillate continuously with this frequency, with applied force frequency. After sometimes it will be oscillate with applied force frequency. The same things it has been written, but after sufficiently long time, but the transient or decreasing of amplitude completed, and ultimately the oscillator performs oscillation at the frequency at applied force, that is called the steady state. That means that means uh, the transient part is going to be decrease and decrease, and after some time the transient part or damping part is going to be vanish from the oscillation, and we are going to get the uh, oscillation after transient state only due to the applied force, and that is nothing but called the steady state. So for this particular solution or steady state, how we are going to be solved, let's check it out. Here for that, let x2 is equal to a sine pt minus phi be the steady state solution of the equation number 2, and phi is the phase difference between the applied force and displacement. Okay, a is the amplitude of the oscillation. So now we have to take the first derivative and second derivative of this equation. We are going to find this and this, and we have to put it in equation number 2. The equation number 2 is this one. Okay, initial equation number 2, we have to put this equation number 2. Then we are going to found like this one form. This is the form. This is nothing, this is nothing. Okay, uh, so like, so it is very simple explain. Mathematics will be there. See, it will be, I have so here first it is written omega square a sine pt minus phi, then this term, then this term, then right hand side term is written in the format of sine a plus b, that is sine a into cos b plus cos a into sine b. Then by solving this, we can found like this. So here a sine pt minus phi, if we are going to take common from these two terms, we can found omega square minus p square plus 2bap cos pt minus phi, cos pt minus phi is equal to f0 is equal to this one. So if we are going to compare the right hand side term with left hand side term, means this right hand side we have sin ft phi, and left hand side also sin ft phi, or we are going to be then what we are going to found, we are going to found a into omega square minus p square will be equal to f0 into cos phi, right? These things it has been written. Likewise, if we are going to compare this cos pt minus phi left hand side and right hand side, we can found 2bap is equal to f0 sin phi. Same thing it has been 2bap is f0 sin pi. This is the equation number 6 and 7. This is the equation number 6 and 7. So squaring the equation number 6 and 7, we can found a is equal to f0 is equal to this one. That day I told that mistakenly I have been forgot that this root over, you have to put the root over. So here phi, dividing equation number 7 and 6, we can found phi is equal to tan inverse 2bp. So this is the amplitude of the forced harmonic oscillator, and this is the phase. Okay. Hence, the general solution for the steady state solution, the general steady state solution will be x2 is equal to a sine pt minus phi. So a we have been found this one is equal to sine pt minus phi. So the complete solution of the equation number 2, that is transient solution and steady state solution, if I am going to put for the equation number 2, then x2 is equal to x1 plus x2 will be this one. So this part is nothing but the transient term which decreases exponential and stopped after long time. See, it has a exponential term, decreasing of exponential, e to the power minus x, means this term is a sinusoidal, it is oscillating but it is decreasing. Okay, but it is, there is no exponential decrease term, it is only sinusoidal, or it is a wave form, uh, which is the so called periodic applied force to the damped harmonic oscillator to found the continuous oscillation. Okay, now the resonance means the phenomena in which the amplitude of the forced harmonic oscillator becomes maximum for a particular value of frequency of applied force is called as the resonance or amplitude resonance. So this is nothing but the particular frequency at which of applied force at which resonance occur is called the resonant frequency. That means you just imagine the damped harmonic oscillator. First, you have to imagine the damped harmonic oscillator. That means whenever you have to start from the oscillation from a mean position or from a particular position, it will start oscillate like this, and after sometimes it will stop. This is called the damped harmonic oscillator. But however, if we are going to give the continuous force to the damped harmonic oscillator, then it will be continuously oscillate. Okay, but at the time of giving force, external force outside to the oscillator, damped harmonic oscillator, the oscillator is gradually increases its amplitude. Okay, so for a particular frequency, the maximum displacement we can found for the oscillator means it is oscillating for a particular frequency. For a particular frequency, the amplitude or the oscillation will be maximum. The particular frequency of applied force, the oscillation will be travel to the maximum, will be travel, this is the oscillation, it will travel maximum displacement. This is called as the resonance condition. The resonance frequency with which oscillation will be maximum amplitude is called as the resonant frequency. I am going to give you a small example. Maybe you have been knew about the Howrah Bridge in Kolkata. There is no support in the middle of that bridge. There is no support in the middle of that bridge. So, we have to imagine that bridge is always oscillating. So any disturbance on that bridge, we can expect, or it is oscillating with different frequencies. Okay, that means heavy truck, heavy vehicle also, if going to be move on that Howrah Bridge, then that bridge is not going to be break. Means the amplitude of vibration is not the maximum. So if that vibration amplitude of that bridge will be maximum, then the bridge can be breakdown. So only for that, if with a continuous periodic frequency force is not allowed on that bridge. Remember, any type of vehicle is moving on this bridge, that is not a periodic vibration or periodic force on that bridge, but a periodic vibration or force if we are going to provide on that bridge, then the bridge will be in the will be in the position that it can be break. That means there is not allowed of marching of soldiers on that bridge. I repeat, there is no allowed marching of soldiers like ek do, the soldiers are marching in this way with same time left leg has to be put and right leg with same time it has to be put. So it will be a synchronized manner of a periodic force. If synchronized manner of periodic force you are going to be apply on that bridge, you are going to get the maximum amplitude of the vibration. That means it is very risky at that time to save that bridge from breaking. So only for that, this is not allowed on that bridge. Marching of soldiers are not allowed on that bridge. So now the previously we found that this is the amplitude of the force harmonic oscillation. If this will be maximum, then it will be called as the so-called resonance condition or resonance frequency. So let it is a maximum means d by dp is equal to should have to be 0, and the so-called p is equal to omega square minus 2b square root over, which is nothing but called as angular velocity of applied force or angular velocity of the resonant force. So if PR is the so-called angular velocity, we know that angular velocity is nothing but 2 pi by t, right? Is nothing but 2 pi by t, or that frequency, the omega is equal to 2 pi into f frequency, so f is equal to omega by 2 pi, so angular frequency is equal to omega by 2 pi. So hence the resonant frequency will be pr by 2 pi, so omega square minus 2b square root over by 2 pi is equal to resonant frequency. But if the damping is very small, suppose we have to consider damping, there is no resistance of air medium or the medium from the medium, hence b will be equal to 0. If b equal to 0, then pr is equal to omega. That means we found that the absence of damping, the amplitude of resonance occurs when the frequency of applied force coincide with the natural frequency of the oscillation. If there is no damping, so in which frequency it is oscillating, exactly same frequency if I am going to give the outside applied force, then it will go to the maximum amplitude. So hence for the maximum amplitude condition, pr is equal to omega. So if I am going to put the same thing, pr is equal to omega here in this equation, pr is equal to omega, then sorry, now what will the maximum amplitude? This will be the resonant amplitude. Now I am going to put p. If I am going to put p here, then what will the maximum amplitude? Then omega square plus 2b square root over, like this. So a max will be this one. So here a max depends on the damping factor. So if damping is very small, maximum amplitude becomes large. So if this will be small, this amplitude will be large. Okay, this is your completed of this unit. So if any doubt, we have to discuss later. You go through the videos, previous videos, and these videos, these all are in your YouTube, and try to revise. And we have to revise, starts our revise from the next class. Okay, thank you.